Hello again. When we started this section of the course, we mentioned how some events have infinitely many consecutive outcomes. We call such distributions continuous, and they differ vastly from discrete ones. For starters, their sample space is infinite. Therefore, we cannot record the frequency of each distinct value. Thus, we can no longer represent these distributions with a table. What we can do is represent them with a graph. More precisely, the graph of the probability density function, or PDF for short. We denote it as f of y, where y is an element of the sample space. As the name suggests, the function depicts the associated probability for every possible value y. Since it expresses probability, the value it associates with an element of the sample space would be greater than or equal to 0. Great. The graphs for continuous distributions slightly resemble the ones for discrete distributions. However, there are more elements in the sample space, so there are more bars on the graph. Furthermore, the more bars, the narrower each one must be. This results in a smooth curve that goes along the top of these bars. We call this the probability distribution curve, since it shows the likelihood of each outcome. Now on to some further differences between distinct and continuous. Imagine we used the favored overall formula to calculate probabilities for such variables. Since the sample space is infinite, the likelihood of each individual one would be extremely small. If we assume the numerator stays constant, algebra dictates that the greater the denominator becomes, the closer the fraction is to 0. For reference, 1/3 is closer to 0 than a half, and 1/4 is closer to 0 than either of them. Since the denominator of the favored overall formula would be so big, it is commonly accepted that such probabilities are extremely insignificant. In fact, we assume their likelihood of occurring to be essentially 0. Thus, it is accepted that the probability for any individual value from a continuous distribution to be equal to 0. This assumption is crucial in understanding why the likelihood of an event being strictly greater than x is equal to the likelihood of the event being greater than or equal to x for some value x within the sample space. For example, the probability of a college student running a mile in under 6 minutes is the same as them running it for at most 6 minutes. That is because we consider the likelihood of finishing in exactly 6 minutes to be 0. That wasn't too complicated, was it? So far, we've been using the term probability function to refer to the probability density function of a distribution. All the graphs we explored for discrete distributions were depicting their PDFs. Now, we need to introduce the cumulative distribution function, or CDF for short. Since it is cumulative, this function encompasses everything up to a certain value. We denote the CDF as capital F of y for any continuous random variable y. As the name suggests, it represents probability of the random variable being lower than or equal to a specific value. Since no value could be lower than or equal to negative infinity, the CDF value for negative infinity would equal 0. Similarly, since any value would be lower than plus infinity, we would get a 1 if we plug plus infinity into the distribution function. Discrete distributions also have CDFs, but they are used far less frequently. That is because we can always add up the PDF values associated with the individual probabilities we are interested in. Good job, folks. The CDF is especially useful when we want to estimate the probability of some interval. Graphically, the area under the density curve would represent the chance of getting a value within that interval. We find this area by computing the integral of the density curve over the interval from A to B. For those of you who do not know how to calculate integrals, you can use some free online software like wolframalpha.com. If you understand probability correctly, determining and calculating these integrals should feel very intuitive. All right, Notice how the cumulative probability is simply the probability of the interval from negative infinity to y. For those who know calculus, this suggests that the CDF for a specific value y is equal to the integral of the density function over the interval from minus infinity to y. This gives us a way to obtain the CDF from the PDF. The opposite of integration is derivation. So to attain a PDF from a CDF, we would have to find its first derivative. In more technical terms, the PDF for any element of the sample space y equals the first derivative of the CDF with respect to y. Okay. Oftentimes, when dealing with continuous variables, we are only given their probability density functions. To understand what its graph looks like, we should be able to compute the expected value and variance for any PDF. Let's start with expected values. The probability of each individual element y is 0. Therefore, we cannot apply the summation formula we used for discrete outcomes. When dealing with continuous distributions, the expected value is an integral. More specifically, it is an integral of the product of any element y and its associated PDF value over the interval from negative infinity to positive infinity. Right. Now let us quickly discuss the variance. Luckily for us, we can still apply the same variance formula we used earlier for discrete distributions. Namely, the variance is equal to the expected value of the squared variable minus the expected value of the variable squared. Marvelous work. We now know the main characteristics of any continuous distribution, so we can begin exploring specific types. In the next lecture, we will introduce the normal distribution and its main features. Thanks for watching.